All right, this is our second video in a series on induction with recurrences. In our first video, we did two proofs, an upper and lower bound, with fairly straightforward, simple inductive proofs. In this video, we are going to do two more, an upper and lower bound, where there might be a little bit more trickiness involved in some of the proofs. So I'll introduce a couple tools, a couple clever tools we can use to get past some of these complications. All right, so in the last video, we did the first recurrence relation, which was a linear time recurrence relation, and now we're going to do the second recurrence relation, which is a logarithmic time recurrence relation. So I've got, again, the recurrence relation copied down for our convenience over here, and then I've got our the theorem we wish to prove, or at least our first theorem we wish to prove. This will be the upper bound, where we want to show that it is less than or equal to b times log n. And again, our goal here is to do this by induction on n, on the variable n. So again, we should start out with a base case. Our base case here. Again, we have a choice. Remember, we have a couple different choices here. When we stated that n is less than or equal to 1 for our base case, that gives us infinite choices, actually. Any negative value counts here as well. But that doesn't usually make sense. Remember, our n's are presumed to be positive, or at least non-negative, because they represent the size of our input. So we expect them to be non-negative whole numbers. So n to the -5 or something like that doesn't seem to make sense, but we might want to try, and our instinct here is to try values like 0 or 1. These are the two most common values that we might have to choose, and actually both of them are going to be problematic for us in this case. Now, why is it? Maybe I'll start out. I like to pretend that maybe I'm a student doing this for the first time, and I don't know what the outcome's going to be, so I might want to try one of these. I might want to try my n equals 0 or n equals 1. Well, if I was going to try, let's see, n equals 0, what would I need to prove? I would need to prove that t of 0 is less than or equal to b times log 0. Now, of course, that's my problem right there. Log 0 is undefined, so that's an impossible. It's impossible to even state that. I don't even know what you're asking me. That's an impossible one. So maybe we say to ourselves, okay, 0 is not a possibility. Let's try 1. What would I need to prove for 1? T of 1 is less than or equal to b times log 1. Now we need to be careful here too. Log 1 is 0. That's 0. That means t of 1 must be less than or equal to 0. T of 1, remember, is c. C is guaranteed to be a positive constant, so that's impossible too. So looks like we need a new option, and in fact, our selection of a base case doesn't work at all. So actually, in this case, 2 is going to work for us, but we do need to be a little bit careful here. And here's where I really want to build a case for strong induction. Now, last video, we introduced the notion of strong induction. In strong induction, we use a deductive proof where we assume all prior cases hold instead of just the immediately prior. So immediate prior, I mean, if we're trying to prove position n, then the immediately prior case would be the n-1 case. And that's the standard, what we call weak induction assumption, is that the last one is true. And if we're going to build this, then we've got something like this. N is going to rest on n-1, and of course n-1 is going to rest on n-2, and we see this going all the way down until 2 rests on 1, and maybe 1 rests on 0. But the goal of our proof is we prove one of these. We prove the inductive bit, which tells us, you know, if the one before us holds, the next one holds. Then after the 0 works, then the 1 works. And again, if the 1 works, then the 2 works. And then induction takes over, and we get all the way up to n, or infinity, if it's infinity that we're trying to go to. And again, that's the structure of weak induction, where each case depends on its immediate predecessor alone. The problem with our current case is n doesn't depend on its immediate predecessor. It depends on one about halfway down the hill. So if this is our n here, it depends on one down here. I'm going to draw a little different tower over here. And let's start with 1. We already decided 0 is not going to work for us. And actually, we said 1's not going to work for us either. So we're going to get 2. Now, to figure out what our values depend on, we need to go ahead and plug them in to this formula here, or more specifically, not the t part, but the n over 2 part. Okay, we want to plug in our n here and see what we get. So when we plug in 2, 2 over 2 is 1, so we actually get 2 depends on 1. Okay, what about 3? Well, when we plug 3 in, 3 divided by 2 is 1.5, but if we take the floor of it, 3 also depends on 1. And this is the first important case, I guess. We're going to see more of them, but 3 does not depend on 2. Okay, this is critical, and it's going to be very important here in a second. Next, we're going to do 4. Plugging 4 in, 4 over 2 is indeed 2. Okay, so that depends on 2. And 5, again, 5 over 2 will be 2.5. Take the floor of that. That gives us 2 again. And you maybe can see the pattern that's happening here. The next two, 6 and 7, are both going to depend on 3. The next two up depend on 4, and so on. Okay, but now let's say we're going to start our proof. If we start our proof and we only prove 2 correct, then that will make sure that 4 and 5 are correct, and actually it will make sure 8, 9, 10, and 11 are correct, because 8, 9, 10, and 11 depend on 4 and 5. But it won't prove 3 is correct, or 6 and 7, or 12 through 15, the next 4. Okay, why? Because those ones all depend here on 3, and we haven't proven them yet. So the upshot of this is, if we're going to prove 2 as our base case, we also need to prove 3 as our base case as well. Okay, 3 as well. All right. Okay, so if we want to do this, we can actually do this in 2 steps. So I'm going to start out with that. Maybe we could do, well, what do we need to prove here? Do these ones even work? Maybe we should double check. 0 and 1 didn't work. What about t of 2? What would we need to prove here? We need to show that it's less than or equal to b. Now, log of 2 is just 1. So I'm just going to leave that as that. One case I have is here. One of my base cases is this. My other base case is, now I need to show that t of 3 is less than or equal to b times log 3. And for the moment, I'm not going to worry about what log 3 is. Okay, it's greater than 1. Maybe that's all that matters. Okay. And actually, we could take both of these conditions and we could say, look, these translate. Remember, before we want to say, well, what condition did this hold? Well, the first one's pretty easy. B just has to be bigger than t of 2. And in case you're wondering, t of 2 is just a constant, so we don't have to worry about that. And then in this case, we actually get b must be greater than or equal to t of 3 divided by log 3. And remember, log 3 is greater than 1, so that's making this thing smaller. I'm going to show you a little technique now. We can use these two. We could even go and plug it in and try and figure out which one is bigger. But what I'm going to do is I'm going to show a second technique here that's going to rely on an important fact too, both that t of n and log of n are both increasing functions. Because they're both increasing functions, we know the following is true. T of 2 is less than or equal to t of 3. This is guaranteed because we're increasing. We also know the same thing is true for log. again, guaranteed because we're increasing. Now, because of transitivity, if we can show this one, and I'm going to draw it big because this is the one we need to show. This is still the question mark. If we can show this one, then by transitivity, we get that t of 2 is less than log 2, and t of 3 is less than log 3. Now, transitivity, let me remind you what that means. If a is less than or equal to b, and b is less than or equal to c, then we know, therefore, a is less than or equal to c. And this is a relationship we're all comfortable with normal numbers. We already know that's true. If we can fill in this last gap here, we get the whole thing for free. So to do that, we need to show that t of 3 is less than or equal to, oops, I forgot my b's here. There should be a b here. B log 2, which again, remember, was just b itself. So I'm going to take all that work that I just did there and compress it into a single statement here. T of 3 is less than or equal to b log 2, which again is just b. And then again, I might say that's b must be greater than or equal to t of 3. And that condition will satisfy both base cases n equals 2 and n equals 3. Okay, so that was a little bit of a trickiness. That was really the trickiness involved in this proof. Hopefully the rest will go fairly straightforward. Let's continue with our inductive hypothesis. All right, so our inductive hypothesis, again, restating what we're trying to prove. But again, I usually rely on the new variable k instead of n. You can pick any variable, but I pick k. So k, and we only want to assume it for the k less than n. Remember, this is the strong induction that I'm talking about. Okay, here we're assuming, so say we're working on number 8 here, we're assuming that all the values less than it hold, which is good because 8 depends on 4. It doesn't depend on 7. Okay. All right, so we're going to do that. And again, we need to be careful here that since our base case covers the cases of n equals 2 and 3, our inductive step is taking over the ones that are left over, all the n greater than 3. Okay, so let's start. T of n. Again, the first step in our inductive proof is to copy down the definition. This one's a little bit different than the last two examples. We now have the floor of n over 2 showing up in there instead of this n minus 1 term. All right, still we want to apply our inductive hypothesis, and again, it's probably important for us to do our double substitution. First, we need the floor of n over 2 to go in. That's going to restate the inductive hypothesis as t of the floor of n over 2 is less than or equal to b times log the floor of n over 2 as well, being very careful to put the whole floor of n over 2 in for k, meaning now we can say that this is less than or equal to, I'm going to substitute out for my t of n over 2 term with my b times log floor n over 2 plus d. Okay, keeping in mind somewhere down below here we want less than or equal to b times log n. That's what we have up above. That's what we're trying to find. So can we manipulate this into that form using some of our tools, our algebra and our other tools? The first tool I'm going to use is a tool to approximate away my floor. Remember, the floor only makes things smaller, or maybe leaves them alone. So we can actually ignore it when we're doing upper bounds. We can do b times the log of now just n over 2, dropping out the floor altogether. It'll only make it bigger if we drop out the floor, so we can continue from there. So now I'm just going to use my log identities to do b times log of n, and then it's going to be log of the top minus log of the bottom. Okay, I'm distributing my b through. B times log of the bottom is log of 2 plus d. And then I guess we've got room for one last line here. Hopefully it's the last one I need. b times log n minus, well, log 2 is just 1. So it looks like we've got, again, similar to our proofs we saw in the last video, we have a negative component and a positive component, and we want to make that last jump, which I sometimes call a leap of faith, to get to our conclusion. And again, it's not a leap of faith if we can verify for when it's going to be true. We want this whole thing to be less than or equal to, meaning we want the negative to bait out the positive here. So let's just say b has to be greater than or equal to d, and it looks like that step will hold. So now I can say, well, let b be equal to, well, what should we have it? I'm going to pick the max of what I have above there, t of 3, and what I have below here, which looks like d. Okay, that's going to be my choice of b. And then I can just finish my proof. By induction, what did we show? We showed that t of n is less than or equal to b times log n for all of our n, greater than or equal to, being very careful here, 2 this time. We didn't get 1. 1 didn't work. Greater than or equal to 2. Okay, so if we want to continue then, completing our theta proof, we now need to complete the omega bound. And I didn't fix this here, so let's fix this. If I want to do the omega bound here, I now need to show that it is greater than or equal to a times log n. And again, I'm going to do this by induction on n. Okay, so let's start with a base case. Let's try some values. Now, we just finished a proof that our base case was actually really painful. But I'm not going to have any post-traumatic stress about that. I'm going to say, let's just try n equals 1 and see if it works. It might cause us the same pain, but let's go in confident and see. What's going to happen? Again, what do I need to show? Maybe let's see if it's going to work for us. I need to show that t of 1 is going to be, what is it? Well, by definition here, it's c. So I know what that is. And I need to show that this is greater than or equal to a times log 1. Now remember, log 1 was 0, and this caused us problem on the other side, on the upper bound. But on the lower bound, we just need to show that c is greater than or equal to 0. Well, that's actually promised to us already. This is actually true, and if we want to say our condition here, oops, this is true for any a. So no condition on a whatsoever. So this log of 1 caused us a lot of pain on the other side, and it actually makes things really easy on this side. So we can jump right into the inductive hypothesis. Again, our inductive hypothesis is going to restate what we're trying to prove, but being careful not to beg the question, restated with a new variable k instead of n, and also for only a limited restricted values of k. The k is less than n, and again that sets up our strong induction. So now we can do our inductive step. Since n equals 1 worked, then that means n greater than 1 is what we need to handle in our inductive step. And we can again begin with our t of n. What is our t of n equal to? Looking over at our definition, we can see it's the t of the floor of n over 2 plus this constant d. And again, down below here, we probably want to get to greater than or equal to a times log n. That's what our proof we're trying to make. Let's use our inductive hypothesis here. If we need to, let's go ahead and write it down in terms of our new variable. T of the floor of n over 2 must be greater than or equal to a times log of the floor of n over 2. Okay, plugging that back in here, we get a times the log of the floor of n over 2 plus d. And now things are going to get a little bit trickier for us. Okay, the next step in the upper bound, the next step was to get rid of the floor, and luckily the next step on the upper bound, we just got to ignore the floor. It just disappeared. But on the lower bound, that isn't true, because it's not true that the floor of x is greater than or equal to x. That's not true. What is true is that the floor of x, or at least the approximation we've been using so far, is that the floor of x is going to be greater than or equal to x minus 1. And if we plug this in, that's going to give us a new term here. A new term is going to be a log. We're going to get n over 2 minus 1. And you'll notice you get this minus 1 inside the log. And that can be a little bit painful. There's no good algebra to help us get that out. There are a couple approximation tools to help us get that out. But I do want to introduce a different way we can approximate this that's going to be a little bit more helpful. For this one, we might want to show the floor of n over 2. We might say, hey, that's greater than or equal to. And our goal might be to do an n over something instead of an n something minus. We don't want the minus showing up there. We want this. And so we might pick a value, and there's a couple that come to mind. 3 might come to mind, but I'm going to pick 4 because 4 is a power of 2. And I might want to verify when this is true. Well, I'm going to plug in a couple values here. Maybe I'll do it here. So say we have an n of 0. Then this 0 over 2, the floor of that's 0, and we get 0. So greater than or equal to, yeah, that works. Let's try 1. Here we're going to get a quarter. But here we get a 0. Is 0 greater than or equal to a quarter? No. Okay, so then 2, here where it looks like we're going to get 1/2. And over here we have 1. Is 1 greater than or equal to 1/2? Yes, yes indeed it is. Okay, so it looks like things continue on at this point. The next point we're going to get 3/4. It's actually going to be true as well. But we can see after this point, after 2, after n equals 2, this is true. Well, luckily these are the values of n that we are handling. So we can go ahead and use that here. We can say, oh, all right, so let's get rid of the floor, or let's get rid of the floor here. I say a times log of, now I'm going to say n over 4 plus d. And then I can use my log identities to give me an a times log n minus an a times log 4 plus my d. And maybe I'll squeeze it right in here. We're going to get our a times log n minus, that looks like 2a plus d, because log 4 is just 2. All right, can we make that leap of faith in the last step? Well, again, we want our second to last line to be greater than or equal to our last line. So we want the positive to outweigh the negative. So if we're writing a little condition here, we want our d to be greater than or equal to 2a. But since it's a that we're picking, maybe we'll switch that around. We'll say let a be equal to. Now we'd normally have to choose between 2, but our condition above held for any a, so we just need our a here to be what? Less than or equal to d over 2. So I'm going to pick, d over 2. All right, let a be equal to d over 2. By induction, so by induction, what did we show? We showed that t of n here must be greater than or equal to a times log n, and we did this for all the n greater than or equal to 1. And that's different than we did on the lower bound. It only worked for 2 on the lower bound, but we made it work for the upper bound, so we're done there as well. Okay, so that concludes our second video on induction with recurrences, and again that will be our second pair of upper and lower bounds. I'm going to have one more video on induction in recurrences, and we will be doing induction in a few of the other videos as well, so we'll get lots of practice with this. But in my final video on induction and recurrences, I'll do the final recurrence relation that we have waiting for us. and I will introduce maybe one or two more little tools or tricks we can use in induction to help us get through this algebra bit at the end. All right, thanks a lot for watching, and we'll see you in the next video.